science. And welcome to our next topic in science. And last week we were discussing nuclear chemistry, which totally ties into our topic this week. And the second part of our topic this week is really the theme of our entire fourth unit of study in science this year. And that theme is, wait for it, here it comes, energy. And this week we are going to be focusing on nuclear energy, which ties into where we began last week with nuclear chemistry. So let's dive right into nuclear energy today as you open your books and get ready to jot some interesting things down with today's topic. So to begin, let's begin with our own state of New Jersey because we are important historically speaking. We have in our own state our nation's oldest nuclear reactor. That's right, you heard it, right here in New Jersey. We are proud of many things in the great Garden State, one of which is Oyster Creek Power Plant. It's down near Toms River, down near the shore region of New Jersey. And again, it is America's oldest nuclear reactor, built in 1969. So it's not quite as old as I am, but it was built by JCP&L, Jersey Central Power and Light, back in 1969. And guess what? It is still operating. It is still generating electricity. And you know what? It's not our state's only nuclear power plant either, because there are others. Here's Oyster Creek down the shore, but we also have Hope Creek and a couple in Salem, down in the southwestern part of our state. So we have several nuclear power plants right here in the state of New Jersey, and they are still operating. Let's see, fairly recently, I'm just reading this, Oyster Creek, for instance, sits on an 800-acre site in Lacey Township. Lacey Township, that reminds me of my old dog. I adopted a dog, and I named her Lacey because I adopted her from Lacey Township, from a place called Popcorn Park Zoo. And she was a wonderful dog. Anyway, moving right along. They generate enough electricity to power, is it 600 or 800,000 homes a year? Wow. So they generate a lot of electricity. What does this say? Interesting. Just days after Oyster Creek got a new 20-year license in 2009, a series of radioactive water leaks were found. Golly. But you can read up more about the nuclear power plants in New Jersey. In fact, maybe we will talk about them in class later on. But let's get back into nuclear energy. We have talked a lot about this topic over the last week. We had a few extra days to watch some videos introducing nuclear energy, so you know quite a bit about nuclear energy already. But in a nutshell, nuclear energy is the energy contained within the nucleus of an atom. I know, it seems almost too simplistic now that you know something about nuclear energy. Nuclear refers to the nucleus of an atom. And of course, we all know what energy is, right? Energy is... All right, for those of you who got it, energy is the ability to do work. or cause change. Remember that from earlier in the year. But the nuclear energy, again, comes from the nucleus of an atom, and the nucleus is the center of an atom containing the protons and the neutrons, those tiny little subatomic particles, the protons and the neutrons. That's where it's at when we're talking about nuclear energy. And you may recall in the last topic learning about the binding energy and the unstable nature of overloaded nuclei, and how nuclear breakdown results in radioactivity, which is where nuclear energy basically is utilized in harnessing that radioactivity in a hopefully controlled manner. Now, it was Albert Einstein who first in 1905 predicted the great power contained in the nucleus of an atom itself. I mean, think about this for a moment. Atoms. Well, first of all, you can't believe them. They make up everything. But all right, no, atoms, the smallest building block of all matter. We're talking about itty bitty tiny little things. You may remember the whole topic we spent learning about atomic models and just how small these atoms really are. But Einstein made this prediction in his theories that even though they are incredibly tiny and have just a very small amount of matter, energy is contained within that very small matter and can produce an enormous amount of energy. His famous equation, E equals mc squared, relates energy and matter. Energy is the E, matter is the M, and I wonder if any of you know what the C is in this equation. C represents the speed of light squared. That is an incredibly huge number. And in this famous equation of Einstein, think about this for a moment. Even a tiny, tiny little bit of matter multiplied by the square of the speed of light, which is an incredibly large number, results in a humongous amount of energy. And so even the small atom with tiny matter can produce unbelievable amounts of energy. And as a result of that prediction and many others, Einstein was designated the person of the century by Time magazine for his famous equation, his famous theories, and how he contributed to science and technology throughout the 20th century. But Albert Einstein made this prediction in his theories, and his predictions came true, as you know, and as we learned previously with nuclear chemistry and radioactivity, and how we talked about the bombs, the fission bombs as well as the fusion bombs. And those are two words we'll discuss more this week. In fact, let's start with nuclear fission itself. As you may recall, nuclear fission with an I refers to the splitting of atomic nuclei into smaller parts. And in so doing, this, as we said, releases an enormous amount of energy. Now, this is relatively, no pun intended with the reference to Einstein there, by the way, but this is relatively easier than the nuclear fusion we'll talk about later on this week. But here we have an illustration of a single neutron bombarding a very large nucleus of an atom of uranium, and that's all it takes for the release of energy as well as the breakdown of that nucleus into krypton and barium, other elements. It's that energy that we're most interested in when we get to this phenomenon that takes place. And it results in, once you get this started, nuclear fission, once you get it started, it can result in a chain reaction. We'll be learning a lot more about chain reactions during the lab on Thursday, but a chain reaction is when a single nuclear fission causes other nuclei to undergo fission as well. It's also known as the domino effect. And you can see how one breakdown of a nucleus results in the bombardment of two more nuclei with the neutrons, and then those atoms breaking down or nuclei breaking down bombard two more, and so on and so on. It's really an exponential growth when we talk about nuclear chain reactions and the domino effect. This is again a very powerful effect that, when harnessed and controlled, can result in an enormous amount of energy. And so let's focus on that for a moment, because when it is controlled, we do so with a nuclear power plant. And a nuclear power plant is a facility like the Oyster Creek facility right here in New Jersey that produces and hopefully controls fission reactions. Fission reactions, and here's a picture of it, but the sentence continues: fission reactions to harness energy. And the reaction releases heat energy. There's an enormous amount of heat energy, which then in turn is used to heat water. And when the water is heated to above the heat of vaporization temperature, it'll turn from the liquid to the gaseous phase. We call it steam. And then that steam, which has an enormous amount more energy than the liquid water does, and you may recall that from when we learned about the phases and states of matter earlier in the year, that steam is used to turn a turbine in order to generate the electricity. So we have a transformation of energy, or a transfer of energy from one form of energy to another form of energy in a nuclear power plant, and this basically is how it goes. In order to produce the electrical energy, we tap into the nuclear energy, breaking down those nuclei of atoms, which generates heat, which then turns the turbines in the generator, which then produces electrical energy. So we're going from nuclear to heat, mechanical to electrical, to get to that end point of where we need. So, I mean, if we think strictly about efficiency here, even though nuclear power plants can be fairly efficient in terms of the amount of waste that is produced in relationship to the amount of fuel that is used, they're more efficient than, say, coal or oil. But still, we're going from one form of energy to another form of energy. And as a result, there's always going to be some loss of energy. But we are all somewhat familiar with the amount of energy in nuclear power plants based on our last topic's videos from last week. So we're going to call it quits here for today regarding nuclear energy, and we'll pick it up at this point tomorrow. So until tomorrow, I'll just say bye-bye.